Welcome to Torque and Angular Momentum AP Physics 1 review. It's getting towards the end of the year, and with the new coronavirus, it's getting harder and harder to be able to complete all of our assignments and learn everything in AP Physics 1. And I'm here today to introduce to you the concepts of torque and angular momentum. Now, this is probably one of the most intuitive topics in AP Physics 1. It's pretty difficult. But the good news is you do know a lot of what's going on, and basically this unit encompasses most of everything that we've learned. It involves momentum that we just learned, Newton's second law, kinematics, almost everything. Okay, so let's jump right in. So here's a little review of circular motion variables before we get started. If we recall back to when we were doing centripetal acceleration and circular motion, we used a couple of these variables. One new one that might jump out to you is angular acceleration. Right here, this is obviously this is a new variable. It's measured in radians per second squared. And it's the rate of change of angular velocity. All these other things should, all these other variables, angular displacement, angular velocity, should be pretty familiar to you guys. And again, if you want to look at converting from linear to circular motion, we have our arc length equals the radius times the angle, and then if we take the rate of change of that, we have velocity equals radius times angular velocity. And if we take the rate of change of that again, we have we have tangential acceleration is equal to radius times our angular acceleration. One thing to keep in mind is there's a lot of accelerations going on. Centripetal acceleration deals with the force in a circle. So if I have a circle right here and I have a force vector going up like this, that's centripetal acceleration right there. If I have that's center seeking, that causes an acceleration due to a change in direction, because the speed doesn't change normally, but the direction's changing. That's centripetal acceleration. Tangential acceleration is our normal, F equals ma, right? That acceleration is just a greater change in velocity or speed. Usually it's just speed. That's what tangential acceleration is. So, and we haven't talked about angular acceleration too much, but that's something new that we're gonna talk about. Okay, so here we have our angular kinematics equations. So from the beginning of the year, we learned our normal kinematics equations. These should be a good review for you guys. And believe it or not, we're going to revisit these equations. We're going to come back to them, but they're going to be in a slightly different form. Okay, before we were talking about, these are linear, right? These are linear notations, or these are linear formulas for angular kinematics, excuse me. But for angular kinematics, all you do is you substitute each of these values here. Change in x is change in angle theta. Velocity is angular velocity. Tangential acceleration is going to be angular acceleration. And time stays the same. Okay, so you might take a guess, and here they are. These are our new formulas for angular kinematics, and we'll be dealing with different problems that involve kinematics, and the problems will be worded very similarly. Again, I'm just going through a quick review, so we won't go through any example problems right now, but it's good to keep these in mind because these will pop up on the AP exam. Okay, here we go. What is torque? You might have heard other people say what torque is. You might have an idea of what torque might mean in your head, but it's time to put torque into a more mathematical sort of definition for you. So the good news is you do know a lot about torque already. what happens if you try to push on a door, right? What if let's say I have a force right here. Let's say I apply a force to the hinge of the door, right? If I apply a force to the hinge of the door, let's give it a magnitude. Let's say this force is going to be 10 newtons, right? This force is 10 newtons. Sorry, that's really bad. 10 newtons. If you apply a force at the hinge of the door, it's not going to move at all, right? Not at all, right? Maybe it's certainly not how you open a door, right? But if you apply that same force over here, right? Let's apply that same force, same magnitude. This is also 10 newtons. All of a sudden, this door will begin to rotate. And this is what torque is. It's basically the force used in rotating an object, okay? And we've already seen how, okay, well, it has something to do with force, and it has something to do with, right here, right, the distance, right? If we call this distance r, we know that the torque has to do something with r, because if you apply a force right at the axis of rotation, that's something we'll be using, axis of rotation, right? It's not going to rotate at all. But if you apply a force, farther away from the axis of rotation, you're going to get more torque. You're going to get more torque, okay, on the door. Here, let's go for a little bit of an example here. So let's say let's say this is a ruler, okay? So ruler's center of mass, we've sort of just gone over this. You can already guess that ruler's center of mass will be right about here, right in the center of the ruler. And so for our purposes, this is going to be our axis of rotation. So if we have if our center of mass is right here, right? And let's say we apply a force. Let's say we apply a force right at the center of the ruler, okay? If we apply a force of, let's use that same value. Say we apply a force of 10 newtons. And let's say the mass of this ruler, let's say mass is equal to 2 kilograms. Obviously, this is pretty heavy. That's pretty heavy for a ruler, but just for example purposes, we'll just use it like that. Now, if you apply a force at the center of mass of an object, this is what we've been dealing with all the time before. F equals ma, right? So we can solve for the acceleration, right? Because it's this ruler. You can guess what it's going to do, right? This ruler is going to move just like that. It's going to move in a straight line, just like that. It's going to move straight, okay? That's what's going to happen if you apply a force, and you can solve for the acceleration, obviously. Now, let's say we have, let's say if we apply a force with a radius r, or distance r, I should say, over here. And let's say r is equal to 0.5 meters. And again, we're going to use that same force. We're going to use that same force of, sorry about that, 10 newtons. Sorry, hold up. We're going to use that same force of 10 newtons, and this thing is going to rotate, okay? And obviously, if you apply the force right there, the ruler is going to start to rotate, and it's going to start to rotate with a angular velocity and whatnot, angular acceleration. It's going to start to angularly accelerate. So all in all, we know that torque, right, has to do something with the force and the distance in which it's applied, right? So let's say so let's quantitatively define torque. Torque is going to be equal to the force, magnitude of the force, times the distance multiplied by sine of the angle between the force and the distance. What do I mean by that? So, so this is our big definition of torque right here. Torque equals Fr sine theta. So basically, if I take away, let's say I apply this force a little bit differently. So let's delete this. Let's say I apply this force right here. And let's say I apply it at an angle. Well, all of a sudden, this is where the sine theta comes in. That's most important. You might also see in this formula written as torque equals F times the perpendicular of the radius, because that's basically the same thing as sine theta. So basically, so if you're applying that same 10 Newton force, right, but it's at an angle, the only angle that matters in angularly accelerating this ruler is the vertical component. So this is going to be 10 sine theta. 10 sine, and let's call it, yeah, okay, let's just say this is like 45 degrees, right? This is going to be 10 sine 45. So that is where the angle comes in, and it's really, that's the only thing. When you have a force that's directed at an angle, the biggest thing to make sure that you keep in mind is that you take into account only the vertical component, because that's all that matters when you're angularly accelerating something. What if you push, let's say you push on this ruler right here. If you push like that, this thing is not going to rotate. If you're going to push on the ruler like that, parallel, right? If I pushed on the ruler at an angle of 0 degrees, sine of 0 equals 0, right? Sine 0 equals 0. If I put a force of if I put a force at an angle of 0 degrees or parallel with the ruler, there's going to be no torque, right? But again, if I apply it directly perpendicularly at an angle of 90 degrees, sine of 90 is 1. That's the max that sine theta can be. Then it's just force times the radius. Okay, that might be a little bit new to you guys, but let's move on. So Newton's second law, part 2. Let's so we know what Newton's second law is. We've worked with it for a while. So we have acceleration equals force divided by the mass. Okay. Now we need to figure out a way to define Newton's second law, right? And see what affects the centripetal acceleration, right? So we don't really know exactly what's on the top and the bottom for here right now. Okay. But we were just sort of introduced to torque, and torque maybe has something to do with the force, right? So let's see what we have here. So let's start with F equals ma. So if I start with F equals ma, and I'm trying to convert this into a circular part of the circular version of Newton's second law, you might be clever and you might think, oh, let's multiply r to both sides. Okay, it's a good idea. So we have force times the distance equals, sorry, let me go back to torque right here. This is measured in Newton meters. Newton meters, this is important. Newton meters, you might think, oh, that's joules, right? We've worked with Newton meters before and we called it joules. No, torque is not a form of energy. So we're just going to leave it as Newton meters. Okay, that's sorry, just to clarify that. So, that might help you with understanding this formula a little bit better. So then we have MRA. Okay, now we might recall from earlier this formula right here. The formula is very important. This is exactly what we were talking about, and this is where it's going to be used. So we have our tangential acceleration is going to be equal to the radius times the angular acceleration, right? And we're going to be able to relate this later on into the video. But for now, we're going to be using, so we're going to be using that right now. Okay, so let's plug that value in for, so we've already know this is torque equals mr times centripetal acceleration times r. And you might be like, oh, okay, mr squared. So you have torque equals mr squared times the centripetal acceleration. Times the centripetal acceleration. So we have mr squared times r centripetal acceleration. Okay, now this looks like F equals ma, except a little bit different. Okay, so what we call now, so let's erase our things here, and we know what the top is, right? We know what the top is. It's going to be torque. This is torque. But what's on the bottom here? What could this be? That's this little mr squared thing here, and we're not completely sure what it means yet. But it's important to understand what's really going on in the F equals ma equation. So mass has inertia, right? And the more inertia something has, it's going to be harder to accelerate. Well, you can think of this value here as rotational inertia, right? How hard is it to angularly accelerate this object? So we're going to call this the rotational inertia, otherwise known as the moment of inertia. And the moment of inertia is equal to mr squared for any point object. And we're going to go, sorry, I'm just going to change this here. Okay, so this is our version of F equals ma, Newton's second law, part 2. Hopefully that makes a little bit of sense for you guys. Okay, what exactly is moment of inertia? It all depends on the reference point. For uniform objects, there are specific formulas you don't necessarily need to memorize. Okay, so basically moment of inertia is going to be, for a point mass, for one point, is going to be equal to m times r squared, which is the distance from the axis of rotation, right? Now, if you have any object, for any object, the moment of inertia is equal to the sum of all of the mr squareds inside. So let's say for example we have a baseball, or let's say we have a ball right here. Right here, there's going to be, here's our center. Right here, there's going to be a little mass right here with a different radius. Here's going to have a different radius. Here's going to have a different radius. All these points are going to have different radiuses. So you're summing up each of these individual moments of inertia about the axis of rotation to get the total amount of moment of inertia of the object. And they're different for different shapes. And there's a bunch of formulas down here that you don't need to memorize for the AP exam, but they might be good to know. But just know the most important thing is that you're summing all the individual masses times the individual radiuses for an object. That's the moment of inertia. And that's basically it acts as mass. Okay, let's move on. Angular momentum. Okay, so let's so we know what linear momentum is, right? P equals mass, momentum equals mass times velocity. These are both vectors. It can get a little bit complicated when you go to vector notation for velocities, but we'll keep the magnitudes. Now you might guess, okay, well, mass times velocity has to do something with maybe our circular motion variables, maybe velocity is angular velocity, maybe converting and stuff like that. But basically the formula we use for angular momentum is going to be L. I have no idea why they call it L, but that's basically just the P, right? It's just the formula. It's just the symbol for angular momentum, and this is going to be equal to mass times velocity times r. Now you might be thinking, oh yeah, because there's a lot of this times r going on, right? If you go back to our torque thing here, or here, right? Rather, you see we have force times r, right? Our linear motion times r equals our symbol for circular motion, and that's kind of exactly what's going on here. MVR, right? That is our formula for angular momentum. And you might be like, I don't really get it, and it's kind of hard. It's kind of hard to understand. I recommend you watch some Khan Academy videos. They do wrap things up pretty well. So let's do the same thing that we've been doing, and let's plug in some. Let's relate this velocity right here. This is still sort of in like linear velocity. I don't really like the way that this is presented. It might not be very meaningful to us, but let's continue on. So we have so let's plug in for V. If you might remember, it's M. V is going to be equal to R times angular velocity times R again, and you might be like, wait a second, here we go again, right? So we have equals mr squared, and we know that mr squared, right, is going to be equal our moment of inertia times, and this looks a lot like this guy over here, right? And this is going to be our formula for angular momentum. And obviously there are different cases in which we're talking about, conservation of angular momentum, and everything sort of applies the same way. Let's do a quick example of angular momentum. So let's say we have a rod. Let's say we have a rod, thin rod here. Actually, that's kind of an ugly rod. Let's just go for a ruler. Let's go for a ruler again. Let's say we have a small ball, right, that has an initial velocity. Say this small ball has an initial velocity of 3 meters per second. And it also has a mass of 2 kilograms. And then also this ruler has a mass of, let's say 3 kilograms. Doesn't really matter though. And let's say this is a perfectly elastic collision, in which the ball stops after it hits the ruler. And so let's say after it hits the ruler, right? After it hits the ruler, it's going to start to rotate, right? And it's going to start to rotate with, an angular velocity, say 2 radians per second. Doesn't really matter. But the way you'd set it up is pretty simple. Conservation of momentum, we've done it before, right? Initial momentum equals final momentum. So, we could have the MV. This is when our linear one makes sense, because this here is moving in a straight line, but it does have angular momentum, which might be kind of hard to understand. Well, you have MVR equals, and again, R is going to be, let's say this is our axis of rotation. R is going to be this thing right here, this whole thing, because that's where it's going to hit the rod. And then obviously we have our formula for moment of inertia, I times omega, and we can substitute values in, and we can solve for whatever variable we might need for the problem. So this is sort of a way that you can set up a lot of these problems here. I mean, I guess I didn't really need the unit. We're not going to go through it, but yeah, here we go. Last part of today. We're going through things very quickly, so again, I recommend that you keep on watching videos and learning on your own as well. So let's say we have let's continue with, say we have a tennis ball right here. Let's fill it in. Say, so that's not going to be a great color of a tennis ball, but whatever. You get the idea. Okay. So we already know what translational kinetic energy is. 1/2 mv squared. This is going to be our linear kinetic energy. Linear. Okay. Now, you might guess, oh, well, it's probably going to be the same thing, but just using our, circular motion variables. And you'd be correct. So, circular version of this kinetic energy is going to be all of our formulas for gravitational potential energy, by the way, are going to stay the same. The only thing that's different here is going to be our kinetic energy. So we're going to have 1/2 times the moment of inertia times angular velocity squared. And obviously, if you wanted to, derive this expression, you could, say, okay, well, 1/2 mv squared. Oh, velocity is just equal to r times omega. That quantity is squared, and then you're just like, okay, yeah, there's the moment of inertia. There's angular velocity, and we're back to this formula here for circular. Now, this is also measured in joules. So let's say we have this tennis ball right here, right? And let's say it has, let's say it's going to start to spin. It's going to start to spin around. It's going to start to spin around in a circle, right? Sorry, these things. So yeah, so basically, this is going to start to spin, right? And it's going to spin at an angular velocity omega, but it also has translational kinetic energy. So it also has translational kinetic energy. So these are both measured in joules. So let's say you were solving a problem and you're asked, what's the total kinetic energy of this tennis ball if it's moving at a translational velocity, which we already know how to do, of whatever, and it's spinning at a rate of, maybe like 40 radians per second. Well, all you do is you add these two up. So you're going to say that the total amount of energy, so kinetic energy total in the system, is equal to 1/2 mv squared plus 1/2 moment of inertia times angular velocity squared. And this is sort of the basis of how to solve sort of these problems. They seem a little weird. This formula might seem a little bit weird since it's got a lot of different variables going on, but they all cancel out, and this at the end is going to be energy. Here's a little cheat sheet for you guys. This relates all of our motion variables, kinematics equations. It goes over some of the stuff that we went over here. Again, work is something we didn't go over. This right here is a good thing to go over. Power as well. These things are good things to look up. But before we go, we're going to do one last practice problem. Let's do let's do one last practice problem here. Okay, we're going to do one last practice problem. And this is just going to involve everything sort of we've learned today, maybe not everything, but a little bit of what we learned today. So let's say we have a tennis or a ball, let's say a small ball right here. Let's say it's connected to a string at the center like that. It's a little off center. Yeah. It's a little bit off center there. So basically, so we have, say, for example, we have 3 masses here. Okay. So there's 3 different masses on this string right here. Okay. And let's say we want to figure out what the total angular acceleration is of this object. We don't know what it is. But something we do know is we know the distance between each one of these is going to be 3 meters. 3 meters, 3 meters. So when we're solving a problem like this, and we know that there's different forces applied to this. So let's say we have a downwards force and then we have an upwards force on this ball. And let's say, and then, we don't know exactly what, we could say these forces have a number, but it's gonna be some value, right? Say 3, maybe 4. But basically, the way to solve a problem like this is you have to understand that torque is present only when you have a force, right? So you might say, okay, well, how am I going to do this? Well, we can sum all the torques here. So 3 newtons times 3 meters, right? So the total torque on the system is going to equal 3 times 3, because that's for this ball right here. 3 times 3, right? Plus, and then we have 4 times 6, because that's the whole entire length of here. That's the radius in our thing there. And you might be like, oh, well, this one's going down. And again, you would be correct. This is a -3. So, and then you have 4 times 6, which is your distance again. So that's the total torque on the system again, and you need your moments of inertia. And again, you can sum each of the moments of inertia up. So you could say, okay, well, I have mr squared. So I have, we didn't assign masses here. Let's say this mass. Now, even though there's no force applied to this mass, you need to include this mass in your calculations. This looks like it's the biggest one. We'll give it a 5 kg. I'm not gonna write that out. And then this is maybe 2 kg, and that's 3 kg. And obviously we'll sum each one. So we say 5 times r squared. Maybe there's a little distance there, maybe like 1 squared, and then ... We're gonna add each of those other ones up, and then this again, torque over. We're gonna have torque over our moment of inertia, which we know exactly is equal to the angular acceleration. Okay, hopefully that was a good introduction to angular acceleration, and hopefully that wasn't too long and boring. And yeah, that was it.